Okay, good afternoon. My name is Pavel Hrabák, and I want to talk about some challenges in train evacuation. Next to me is Hrabák, who did most of the coding and served as a IT support, so now he is here as a question and answer support, actually. So just to introduce the problem, we did some experiment with railcar evacuation. We did the Pathfinder model and encountered several challenges we want to share with you. So we are sharing what we find interesting. We will be glad for any ideas. Thank you. What is interesting, so I know what he will do for the next year. Okay, so here, a team of 4 people working here, except next to us 2. There are 2 people you can notice, then only Hanna Neymanova is involved in fire safety, and the 2 of us are involved in random processes and statistical physics, okay, which may be important later. The study leans over a full-scale evacuation experiment we did in 2018. We tested several boundary conditions, 5 different exit widths, 3 different exit types, and experimenting with crowd composition. That means not only a homogeneous crowd, but even a heterogeneous crowd involving kids and seniors, etc. So it was altogether 30 evacuation scenarios, maybe too much degrees of freedom, so we did only 1 trial per each. We were interested in total evacuation time from the signal to evacuate till the evacuation. That means we didn't consider any pre-evacuation time in the studies. And for the comparison with the model, we used the occupant evacuation curves. That means the y-axis is the time of the first, second, third evacuated person. So maybe a bit unusual, but very handy for our purposes. And okay, we wanted to support the simulations by Pathfinder, by means of Pathfinder model, which we found out that corresponds to the experiments quite well. And we used the model to support the conclusions drawn from the experiment. But as I said, we encountered several issues I want to share with you. So I would say that there are 3 main challenges in the train evacuation. The first one is a cramped interior, narrow aisles, seats covering at almost half of the area of the evacuation. We were discussing here problems with seatings before. Of course, a non-standard exit path, especially the drop to the ground level, 750 millimeters drop, so how to model such a situation. And of course, the seating positions are not problematic to model, but they define the initial positions of the pedestrians, which might be a problem once you want to randomize the initial positions when the coach is not completely full, occupied. So solving these challenges, we have found out that there are actually 3 sources of randomness. And put a statistical physicist to a source of randomness, he wants to control it, he wants to know about it. So how to describe those 3 sources? Okay, there definitely has to be a variance in evacuation time caused by different seating positions. So when the people are differently seated, it somehow affects or partially determines the order in which the people are in the queue and are exiting, which affects the evacuation time. However, even when you say, okay, you have here the very identical seats as before, which we did in the experiment, you take the identical composition of passenger types, you still have variation in evacuation time, which is caused by different properties of the agents. What is the desired velocity of the people sitting here, which may change, etc. And even with you put your identical passengers to identical seats with identical boundary conditions, you still get a variation in TET because there is some inherent randomness in human behavior. So, okay, this is what we know, and we wanted to find out how to capture this in Pathfinder to be able to control it. So I won't go much to detail, but what we did is we were meddling with the input file. Every time I asked for the license, for the academic license, I check that the best what is about Pathfinder is that you don't have to code anything, and you have the graphical user interface. But then you have to, meddle with the input file. So what we did is we created the model using the interface and took everything but the occupant. And what Uri did was a Python script which generated the occupants for us with the properties we wanted to have. And controlling these sources of randomness means generating random seeds. From the CSV file we found at the very beginning, changing the random parameters and keeping everything else. That means, we were changing maximal velocity and agent diameter, I believe. And of course, the inherent randomness, I don't know how it works inside of Pathfinder, but it is given by random seed and priority level, which is randomly generated. So what we managed to do is we kept everything else intact, only changing these properties which gave us a different trajectory of the process. So this is what we did. This enabled us to repeat the simulations, the very same simulations in the four cycle without the necessity to do it manually and evaluate it manually. Okay, once we have came with those sources of randomness, we wanted to check what it does. So here are box plots for 3 different exit width, 65 centimeters, which represents one line exiting through the door, 90 centimeters, which allowed the staggered motion of pedestrians, and 1.34, which was the actual size of the exit, which enabled 2 lines next to each other. And we were changing the positions, the random seeds, and the velocities over there. You can notice that for the 65 centimeters wide exit, the variance of the evacuation die is comparable. For 90 centimeters, it is maybe a little bit higher for all sources of randomness, probably caused by the higher amount of interactions between agents. But once you have 2 lines, then the randomness, the variance of the seeds almost vanishes. The variance caused by different velocities and change the velocities shrinks. But what becomes more significant is the randomness or the variance caused by the sitting positions. So this is a study of those sources of randomness. Well, small study, but yet. And now to the challenges. So the cramped interior layout, as was said here before, we omitted the seats as well in the train, and it was not only the simplest way, but it gave even the most realistic results, because there was some preliminary research how to model those seats in a train, and the best solution was to omit it. So the seat positions are only for the initial positions, defining only the initial positions. The agent diameter plays an important role because, as I said, we involved the heterogeneous crowd as well. And the heterogeneity was defined by the desired velocity, by agent diameter, and some ability to overcome the jump. So we associated the cylinder diameter with the shoulder width of the agent measured during the experiment, which helped us to model like people, adults carrying a toddler, or people with crutches, etc. However, then you find out that your agents are too wide. So you need to a little bit play with the squeeze factors and reduction due to narrow geometries, etc. Just to to let them evacuate, not to let them stuck. Another relying thing is that we try to simulate the homogeneous group with the default setting, and we found out that it actually significantly overestimates the evacuation time. So we said, okay, so there is a mean speed of 1.19, which is a design speed, so it is not a surprise. So we tried to put there free space mean speed 1.34, something like that, and still it overestimated the evacuation time. So, okay, we wanted to support the conclusions because there was a recording of the experiment even when people were going in. We measured the movement speed of passengers walking in the ASIL, 0.94. So we said, okay, so let's this be their desired velocity with the fundamental diagram turned off. So this is a cheating, I know, but it opens an idea of how to overcome such issue in such a cramped environment. Maybe some research would be needed for such situations. The non-standard exit path, the jump, here the heterogeneity came into the role because it was no problem for passengers without any limitations, no delay at all. However, there was some hesitation and balance delay for the passengers with limitations, and it was different for different type of the limitations. So how to deal with that? Okay, again, we did a trick, just defining behavior. Okay, go to a point before the exit and wait there a bit, move further behind the exit, wait there a bit, and continue with the hesitation and balance delays measured from the experiment. Okay, it helped us with the study. However, it's not the systematic solution because it works only once you have one exit. It does not allow any exit choice. So if you have a better idea, please let us know. Okay, and the last one is the influence of seating positions. We were studying the influence of seating position for different exit width and exit types, etc. There was quite high variance. What is the main results I want to stress is that the experimental seating configuration always led to the significantly shorter evacuation time than the bulk of the simulations. Because the seating in the experiment was somehow inspired by the spread of the pedestrians in the suburban trains we had, so it was pretty much an ideal stuff. But you want to somehow change these initial positions, etc. So there is maybe a space for some research. Okay, what is the possible and realistic initial seating position based on some, I don't know, internal energy derived from inter-passenger gaps or whatever? Because once you generate the initial positions uniformly, you get unrealistically high evacuation times because you have a lot of people in the low deck and almost nobody in the upper deck, etc. But okay, how to do it elsewhere? Once you don't have the information, you should stick to the minimal entropy principle, which is the uniform distribution. So, okay, I think I don't have much time to discuss the global sensitivity analysis, but what I said was supported by the global sensitivity analysis, especially when the exit width was 1.34. The probability of choosing a lower deck seat played comparable low to the mean velocity of the passengers. Okay, so more details maybe in the paper. So to conclude the work, I want to stress those two things that might be object to the future research, is that maybe in such a cramped environment, it would be good to study the velocity-density relation, because maybe it is too strict for this corridor and nasal-like movement as it is designed now. And of course, the seating position and some research on the seating position, how people are choosing the seating position would be beneficial for such a research. Okay, so thank you for your attention.
Do we have any questions in the room? One? Okay. And we just do this one. We have 2 more talks, so we want to get up to our event.
So I understand that you considered the evacuation into a platform or non-restricted area. Did you consider also for tunnels where you have a certain width of a walkway?
No, we just considered a open platform where people dissolve and do not affect each other. The evacuation using stairs and the jump, and there were no other restrictions. So, like the open reservoir of space after that.
Okay. Well, thank you very much. With that, we'll move to the next speaker.
Okay.
Thank you.